Good morning. This is Glenn Dane from Ohio State University, and today what I want to tell you about is a project that we're doing through LIFT, the Lightweight Metals Institute from the Manufacturing USA Institutes. And this LIFT, by the way, stands for Lightweight Innovations for Tomorrow. And we're going to tell you today about metamorphic blacksmith and metamorphic manufacturing, or robotic blacksmithing. And let me pull slides up. Okay, so what I want to talk to you today about is a project through Lightweight Innovations for Tomorrow, which is the Institute for Lightweight Metals established under the Manufacturing USA Institutes. This is a project we have on metamorphic manufacturing that we also call robotic blacksmithing. My name is Glenn Dane. I'm a professor at The Ohio State University, and I run the Agile and low-cost processes pillar for LIFT, Lightweight Innovations for Tomorrow. This is an idea we think is very important. And when you think about metallic parts, there's really two things that are really important. One of them is the strength of the part, making things that are high strength, high fatigue resistance, highly durable. The other is the shape. And if you get shape and strength together, that's really where you win. All of that starts with how we process materials. It's how we end up making things leads you to strength and shape. In this lecture, into all of the various processes. It'll start is ores. They come out of mountains and places like that. We end up taking the oxygen off, reducing the metal, reducing it to primary metal. Then we start with casting. We always start with molten material. The molten material is poured, and one of two things can be done. We could either make an ingot, which is a fancy name for just a big honking block that we further reduce or somehow make use of, and I'll say something about. Or the other thing is we can cast it to shape directly. This is a very efficient method. Ingot also can be fairly efficient. In order to get good properties, what we really want to do is we want to work the metal to make very small crystals. This is a cross-section of a piece of metal that we've polished and put a little bit of etchant on. And what you see are individual crystals that we call grains. The grain size is very important. The composition of them is important. We also often put little particles into what we call precipitates that give strength. And this structure is where the material, the metal strength comes from. And it's that internal structure that matters, that comes from working. And we can work the material into sheet, we can work it into bar or plate. We can also get shapes by machining, basically taking a big block, putting a cutting tool on it, making chips out of everything we don't want there. And that doesn't improve the strength, but it does give us shape. A way we can modify both the shape and the properties at the same time is by plastic forming, working the material with tools like this. This is what's called open die forging up on the upper right. The other thing you can do is sheet forming, basically roll out a sheet of metal and make metal sheet, and then that sheet can go into big tools like this, go into big presses, and you can make parts very quickly this way. These presses run at several hits per minute, because you use ka-chunk, ka-chunk, ka-chunk every time a part is made. Makes it very efficient, but the real problem is by being so efficient, you also need massive tools, massive dies to do that. A lot of money goes into making the tools and the dies, but you can make all of these parts that you see down here. The other way you could do things that I want to mention for completeness is you could take this metal, turn it into a powder. If you make that powder, you could consolidate that powder. You could do it with a laser. That's it. You could make additive manufacturing that way, and again, make all kinds of parts. And then those parts have to be assembled into something, and then welding and joining and all that is another terribly important aspect of all of this. And these are all things that we cover within our Lightweight Metals Institute at LIFT. Key issue in all of this is cost, and cost actually usually mirrors sustainability. If we value energy, we can find that there's a really strong correlation usually between price and the amount of energy you've got to put into something. So if you study any economics, you find there's usually two parts of cost. There's a fixed cost and a variable cost. So you think of what we were doing back here, the fixed cost is to make your first part, you need all of these dies, you need engineering to go into these dies, you need presses available. All of that is terribly expensive. So your first part costs you a lot, and then you've got some variable cost on top of that, which is how much material you have to put in, how much lubricant, all of those things that add up. And the world is remarkably efficient these days. It's amazing how little it actually costs to buy a lot of things. What we want to do these days is very often we want small groups of more customized things. That seems to be the way the world is going. Rather than making billions of something, and there are exceptions to this, iPhones, there's only a few models, but very often we want small custom batches. If we can do small custom batches, we can have everything unique. Fixed costs might go way down, and then it's all your variable costs, and that would be kind of a good thing. And the technology I'm going to talk about is a way of really reducing fixed costs, and also fixed costs making dies and things like that. It takes a lot of time. And we'd also like to keep the variable cost fairly low. If you think about additive manufacturing, you have to go back and make powders, consolidate those powders. That leads to a fairly high variable cost in additive manufacturing. Another key issue is quality assurance. We want high quality parts to come right from the beginning. We also want to make sure that it doesn't take a long time. We've actually got places to buy the things we need. That's a significant issue. And then, of course, as I've tried to make the case already, and you can read much more about this, material structure leads to properties, and to the extent we can, we really like to try to keep the material structure good and lead to very good properties. So what I want to talk about is a way we can really reduce this fixed cost, and there have been ways we've done this in the past. And it looks like there's a big fixed cost associated with this. Is CNC machining. Once you have a CNC machine, you can make all kinds of parts. Here's an example of a turbine rotor of some sort that you can put in a path for this, basically put in code, and this machine can start churning away and make one part, many parts, what have you, and all you need is code to do this. There's no fixed tools once you have the investment in this big equipment. One point I want to make is this was what is the first wave of what I'd call digital manufacturing. Right after World War II, really serious research started on how computers could be used to control things like milling machines, to make different parts every time and make them very efficiently. This was the first wave of digital manufacturing, and it still goes on today. We're still figuring out how to make tool paths more efficient, how to make chips more quickly, how to make shapes more effectively, and it's a fascinating area, and again, started back in the 1940s, and again, huge computer that has far less computing power than an Arduino or an iPad, is used to control all this multi-million-dollar kind of program that's had great impact. That was the first time we've really put computers and machine tools together. The second big wave that's been a big deal, is a big deal now, is what we call digital addition. Additive manufacturing started as rapid prototyping was the name for it. Now 3D printing is what we often call this. And again, this goes back really to the early 1980s. People tried to figure out how to do this, by adding weld wire, sometimes by doing selective laser sintering. And this is stereolithography, one of the first. This started back about 1987. GE has made huge investments in this. I think a big step along the way was about 2009. MakerBot came out with this cupcake. It was about a $1,000 unit. Got this into homes. A big deal, and now we have large deployments, many parts being made, much hoopla out of this. One of the issues with this is almost always we start with metal powder to do this, and when we start with metal powder, you're actually starting with very expensive feedstock, and it's also difficult, not impossible, but difficult to get really optimum material properties out of that, because you're starting with powders and there's only so many materials and so forth that you can use. So that was the second wave. What I want to propose to you today is that there's a third wave of digital manufacturing coming forward, and that's what I call metamorphic manufacturing. And on the left is the past, on the right is what we see as the future. The past, we had blacksmiths who could make almost anything. They could make suits of armor, they could make really cool weapons, swords and so forth, all these things. Horseshoes were a classical thing that they made. And what's really significant with this is how simply this was all done. You just needed a smart blacksmith, a lot of skill involved with this. He wields a hammer, and you've got an anvil, and then you've got some kind of a source of heat. I understand dragons were very popular back then. The other thing you could use is also, obviously, just a well-stoked fire was very common as well. Blacksmith would use his eyes. He might measure things as he goes. He had an idea what kinds of processes would lead to good materials. But there's a big problem with this, and there's a reason we don't use blacksmith parts in airplanes and so forth. Blacksmiths have good and bad days. They can't really have a very strong record of what they did, but you can make all kinds of parts. You can make pretty good parts, but you can't be really assured they have great properties. Therefore, you're not going to use them in demanding applications. Well, what we see on the right is where we think this might be going. Imagine you have the same horseshoe, but now you've got the horseshoe robot. The robot could be married to a press. You could put different tools in this press, and instead of the hammer doing the squeezing, the press can do the squeezing. You can also have heat coming from lasers of some sort, or induction heaters, or any number of ways of doing this. You can also have sensors measuring temperature and shape and microstructure. And beauty of this is you can make all of these parts that a blacksmith could make in principle. Nobody's doing this yet, but you can do all of that, and you can capture all of the data. You can know everything about how that part was made, giving you a great digital record of how to make the next one. Again, the blacksmith proves this is all doable, and with modern innovations, this is something that we think can go quickly and can become a significant new industry soon. So this is really a revolutionary way to make stuff. Again, we can make very high properties materials. We start with standard materials, high-grade materials. If you watch, something like Forged by Fire, you'll hear these guys obsess about the kinds of metal that they use. We can use all these kinds of metals. Blacksmiths know how to do this. Machines can know how to do this. We metallurgists know how to do this. We can get very high properties, wrought materials, worked materials, generally the highest strength and toughness. We have a wide range we can use. Blacksmiths are very clever at heat treating to get tailored, locally tailored properties. Good example is things like samurai swords. They have a very, very hard edge on the front with a tough back. Allows you to have a sword that is very good cutting ability, holds an edge, but is not brittle. Again, we can have automation to collect data, make sure we're doing everything right, and then you can do quantum leaps over what blacksmiths can do today. Blacksmiths operate at about 1 horsepower, if that, half a horsepower. So robots can be orders of magnitude more powerful in terms of force and energy. They can work 24/7, and so things like this should all be doable with blacksmiths, with robotic blacksmiths, with much greater efficiency and much greater properties. So if we think about how we do this, and the idea is rather than adding or subtracting, we're changing the shape and we're changing the properties. That's why we call this metamorphic manufacturing, because we're changing the shape of the properties just like metamorphic rocks change properties. And if you get into the way we do plastic deformation of materials, there's some fundamentals, and all of this has been done with plasticine. Plasticine, which is basically modeling clay, has been used for decades as a physical modeling material for forging processes, where people might work out on a desktop or laboratory how something might work. Key aspect is volume is conserved. A geeky way of putting that is the sum of the 3 principal strains has to be equal to 0. So if you squeeze in 2 directions, you extend in the 3rd direction. That's what that means. And blacksmiths have taught us that we can make virtually any shape we want by a combination of squeezing and bending. Another rule we kind of came up with is primary deformation is more important than secondary deformation. I'll tell you what I mean by that in this 3rd panel over here. Um, One thing that this also gets away from is we've had a lot of work in the past with closed die forging, and always the goal in closed die forging has been to go from a large number of steps, a large number of tools. Each one of these things represents an operation or a tool. You try to reduce the number of operations to get from this shape to that shape. Well, instead of this, we're going to do this with open die forging. And imagine we want to go from something that's like a sphere to something that's like a cube. The way you could do that is basically use this idea of primary deformation being more important, squeeze it down, and you'd flatten the top and bottom of this, but you'd deform the sides. What you could do is take that, rotate it. Again, you'd get some curvy sides, but you'd flatten these faces or these faces again. And if you keep doing that back and forth and keep changing side to side, pretty soon, because you're conforming the top and bottom, you get something that approximates cube really quickly. Any good third grader could take a bit of silly putty or plasticine, Play-Doh, and use a couple books and a desktop to make something that looks like a cube. It's not that difficult. Making those shapes isn't hard. What is hard is going back, measuring and correcting, and so forth. So this is an approach to manufacturing that hasn't been done, that we at Lift think should be done and can be done fairly easily. So in order to get this started, Lift offered what we call the Lift Prize in robotic blacksmithing, and we put up a $50,000 prize purse, including $25,000 for the first prize for any student group. We tried to publicize this pretty widely. For any student group who could come along and make 2 of these 3 shapes using an automated system where there'd be no touch and no, it would all just be done by code. And we picked a classical horseshoe. We also picked a kind of a randomly made bracket, and we also picked a goblet. And this is the approach that turned out to be the winning approach out of Alex Koenig, Booby Near-Duty, and Brian Thurston from Ohio State. And there's a lot of detail on roboticblacksmithing.com. But this is a CNC machine tool, CNC mill. They built this thing called the Honey Badger assembly onto. This turns, the mill goes up and down. This is all controlled through a computer program. A computer program writes G-code, coordinates the motions of this, and this is basically squeezing this block, started as a sphere, to make this bracket shape. So you can see those two custom built squeezers are coming down doing that. You have flattening it out using that primary deformation to get close to shape. Septum feature. And all of this actually can be applied to metal just as well. You need much greater forces, but it's very easy to actually figure out how to run a system to do this. Now you're going to see a tool change where they're going to try to make this feature here in the top. They're going to grab a tool. The tool actually has a much smaller diameter than what you see here, and they're going to go down and starts to dance. And again, all of this is autonomous. The program has been written to make the shapes, and then you just hit the execute button, and by deformation, it ends up making the shape. And again, when you start making that hole, you're going to put some subsidiary deformation around it, but you can go back and again, like a blacksmith might, go back and correct the shape. And that's what you see here is a shape correction exercise. So with that, we've made this first bit. And I want to just also emphasize how impressed I am with what these kids were able to do. They wrote the software, developed the tooling, and programmed it and made it all run. The next one they did was they also made the horseshoe. And again, the beauty of this is it's simply by changing software, you could make something completely different. And this is for making the horseshoe. And again, they're going to start with, so again, you started with a sphere, started working it down to something like a cube. And now basically you've got to start making it narrow and skinny, and that's what you see happening here. And again, because you're taking small bites, small area each time, it's very easy to imagine using a higher force actuator. And if you take small bites each time, you don't need a terribly high force actuator. You can make this out of metal quite easily by hanging a hydraulic press there instead of a plastic and motor-driven element like that. So you see it making each end, it's going along, squeezing, moving towards that approach. It's interesting, I had put onto the Robotic Blacksmithing website an alternate way that I would make this. There's many different ways of making the horseshoe. That's what's interesting about this. The way I would have done it is actually taken a sphere, rolled it down like a hot dog like this, and then basically stamped out that hot dog, bent it, and then put the indents in. They used a different approach, which is completely fine. And again, do the tool change, and that's used to put those in. The tool change can be used for lots of other things. So anyway, again, it's roboticblacksmithing.com. There's a lot more data, information on this. But this, again, proves the concept of how we can use machines to do deformation, introducing what we call the third wave digital manufacturing, which is reshaping materials and improving their properties as we go. So what I want to say is that this leverages a lot of ideas that have been around for a long time. We're leveraging ideas with open die forging, cold die forging. There's all kinds of methods out there. I'll show a little more detail on this for bending and squeezing material. We have great technology for thermomechanical processing for optimizing strength. Closed loop control is out there to allow us to stop machines at precise dimensions. But what's new about this, and there's some technologies coming on really fast that make this a reality, or can make this a reality in a hurry. We have structured light and other methods for fast optical dimensional sensing to see if you've got errors and going back and fix dimensional errors. We've got fast thermal sensing to figure out if we're hitting metallurgically important temperatures to get great properties. Simulation and computation can happen real time to help us correct for any errors. Robots are getting very cheap, very capable. And then also that part that's the blacksmith's brain can also be replicated by machine learning. Machine learning is something that's coming on very quickly, and you can actually have a robot learn how to play games like Frogger or Pac-Man without teaching any of the rules. They just figure it out. They can do things with blacksmithing as well. So all of this is coming together. I expect this will be a technology that we'll see fairly soon. And again, lots of benefits with this. I've tried to talk about this from the beginning. We can make complex forgings without hard tools. You can do very small presses because you take small bites. You can measure everything. It's reproducible. You can get locally optimized properties. Production is local and on demand, and that's actually a big deal. If you look at the energy consumed in making stuff, all of the shipping that goes on to get ore from one place to where the ore is made, get the metal where it's made, to where a factory might be, having a factory in Asia for things that are consumed in the United States, all of these things add to carbon footprint dramatically. And if you have local on-demand production, that can really reduce carbon footprint by making things. We can make things to aerospace standards by data capture, and again, machine learning can help us. It can help us move this along quickly. There's also a lot of needs in order to make this a real technology. We've got to integrate presses and robots. We've got to learn how to do closed loop forming to shape. We need to be able to do machine learning. We need to look at new forming presses and machines. We need to do integrated computational materials engineering real time. These are all things that are very doable, but require some work. We need to figure out how to optimize our process routes. Geeky, detailed ways of talking about this. We have to minimize redundant work, minimize damage, and we also have to develop some recognition and support for this area. Huge amounts of money are going into things like additive manufacturing right now because it's the hot thing. It's important this a hot thing. So again, this is about what we think this should look like. Simply, we've shown the process works, a robot holding a tool with possibly a press, possibly tool changing on it. And then, of course, to make our high value component, we need modeling simulation, we need machines, we need ways of heating and cooling, we need good sensors, we need position control. All of those things are out there, but they need integration. It's not so much a deep research problem. It is a problem of synthesis of good ideas and bringing together the skills, knowledge, and ability to make this important, make this a real area. Again, with respect to how we shape metal, there's lots of interesting things out there that can be built upon. Sheet metal, we can work with incremental forming. This is an English wheel. It's also been used by craftsmen to make very interesting things out of sheet and without tools or dies. Machine learning could be used for that. Some very interesting work going on in Germany using, again, robots and presses. It has part of the vision, but I think they're not thinking very much about microstructural control and standards. There are shrinkers and stretchers that can be used to change flanges. This is all for sheet. For bar, there's many interesting properties, many interesting processes going on. Again, using robots and presses together has been thought about. There's rollers, there's CNC bending that goes on. For bulk, there's lots of things, including automated tool change. You can have hammer forge presses that are powered hammers. Power hammers is the word for that, as something that is important. Axisymmetric is important. You can make things by rolling shapes. You can do this axisymmetric or non-axisymmetric. Some interesting work going on with profiles. There's a little company down in Wichita that's doing some very interesting work with this. There's also some very interesting things going on in Germany and in Dortmund and so forth. One of the processes that's coming along very quickly is incremental sheet forming. This is, again, has part of the vision. It's usually done cold right now and is usually done just with these tools. I think there's ways of really innovating the kinds of tools that are used with this. There's a company called Amino that's based out of Japan that has shown you can make things as complicated as human-like faces or automotive repair parts. There's a very strong research group under Jane Cow at Northwestern University where they've been working on double-sided incremental sheet forming. Point I want to make with all this is that this area is moving along. There's some very interesting work that's going on to validate some of the core concepts. We expect this will get another shot in the arm soon. Lift is investing strongly in some great equipment. They'll have a couple of robots. They'll have presses that sit with it. So again, we expect to use the lift. And the lift, by the way, is a huge institute in Detroit. Lot of room out back. We play football back there, but instead we're going to use it for presses and robots and metalworking equipment. And again, that'll be something again that could put this whole technology forward by putting furnaces, presses, robots all next to each other. Another thing I want to point is just kind of this integration of machines and learning and algorithms and sensors and all of this. This is another thing that I think shows that a robotic blacksmith can do things, taking over where humans have been. If you've ever seen Japanese sumo robot wrestling, this is something you should probably look into if you're into these geeky things. Just put it on and comment on it as we go. But again, you've got these little robots with computers in them, lots of sensors, and these are all making decisions. And basically the rule is one robot tries to push the other off, and it's all done by the robots making their own decisions. This is not sped up. This is how fast robots can think and learn and act. Blacksmiths should be able to do very much the same sort of thing, making these decisions moving forward. And you can see it's all done with something that weighs about a pound or so, and stalk and attack. And again, the idea is to stay within the white lines. And you can see with the sensors that the robots are able to react quickly enough. And again, robot blacksmith with high-speed hammers that would take more power than a human might usually require is something that's definitely should be fun and doable and important. Again, there's some awesome stuff on YouTube. Japanese robot sumo. This is one of these days if I develop a little time, I'd love to have a hobby and make these little sumo wrestlers. So anyway, this is near the end. What I want to say is blacksmiths have made the case very strongly that this is all doable with very, very simple, crude tools. They've made amazing things that you see on the right. As we move forward, there's no reason to think we can't do everything a blacksmith could do, but do it in a much better way than we could, and extend the capabilities. Last slide, and I'll provide all these slides also, is this is all done through LIFT, Lightweight Innovations for Tomorrow, the Manufacturing USA Institute, and this is somewhat described under the novel agile processing pillar. You can see our link there. Again, this builds off things like open die forging, closed loop control, incremental forming, three-dimensional measurement, thermomechanical processing. This is really all of process metallurgy, which is a massive topic, but there's a couple starting points you can see with links there. And lastly, I just want to invite you to ask me any questions directly. My name and contact information is down there. And most of what we work on is impulse manufacturing. You can see what we do at our link there. And this is, again, I think something that can be one of these working tools that works into all of this. So thank you for your attention, and look forward to any commentary that you might have.